Hey everyone, Ravin this side. I hope you guys are doing great. So today we are going to learn about an algorithm which is based on search pattern, and an algorithm name is KMP algorithm. And the difficulty of this algorithm is medium. But trust me, if you don't have any idea about this algorithm, this problem is really hard. So let's read the description. The description says, given two strings, one is a text string txt and other is a pattern string pat. The task is to print the indices of all occurrences of the pattern string in the text string. That is, we have been given two strings. One is a text string and is a pattern string. Now we have to find all the occurrences of pattern string in text string. Use zero-based indexing while returning the indices. That means we need to send result in zero-based indexing in an array. Okay. The note point says return an empty list in case of no occurrence of a pattern. That is, if we don't find any pattern, we need to return an empty list. Okay. So the problem description is very clear, right? Now let's see the example. In the example 1, the text is ABCAB and the pattern is AB. So here the output is 0, 3. So what does this indices represent? From index 0, if we try to match the pattern AB, it is matching with our actual pattern, right? And at index 3, if we try to match the pattern, it is matching again with the pattern, right? That's why the output is 0, 3. In this example, the text is ABCESDU and the pattern is EDU. So the output is empty string. That means we didn't find any pattern matching in the text string. Okay. And finally, in our third example, the text is this and the pattern is AABA. The output is 0, 9, 12. So if we check from index 0, the pattern is AABA, which is matching with our pattern, right? And from index 9, if we match the pattern, the same. And at index 12, again the same pattern, right? So that's why we have an output this. Now, what is the first thought that comes in our mind? Simply consider the pattern window and try to match the text window of same size with pattern. Okay, that is, if the pattern window is 4, we need to cross check every window of same size in text, right? So let's start the execution. First, we'll start from 0 to index. We'll check whether the window is matching. Yes, the window is matching. So the output is 0. Okay, and we pushed it in our result. Now we'll move our window by one step. Okay, now we'll try to match with this pattern. This pattern is not matching. So we'll move again one step. Now this pattern, this is not matching. This not matching, not matching, not matching, not matching, not matching, not matching. This is matching, right? So here we can see the pattern is matching with the same text window. So we outputted the window now here. Okay. Again, we'll move this window by one step. Again, we'll see this is not matching, and finally this is matching. So this window and this window is matching, and the index it is starting from is 12. So we have outputted 12. So what we have observed, we can directly code it up, right? So let's see the code. So here's the code in C++, although the logic remains same, right? So the function name is search, and we have been provided with two strings, pattern and text, and we have to return all the indices in vectors. That is nothing but an array. So firstly, I have taken pattern size in n and text size in m. Okay, then I have created a result vector, right? After that, I'm looping from 0 to m minus n. Now, why this m minus n? Because as we have seen, the pattern can at max go till 12th index. It can't go till 15th index, right? If we even go to 13th index, then it is getting out of bound, right? So the maximum we can compare is that till index 12. If we subtract text length and pattern length, that is nothing but 16 minus 4, then we'll get 12. And that was the last index that we were able to match, right? So we'll run our loop till m minus n. Okay. So in every iteration, we are taking the substring of text starting from ith index till the length n. And what is n? N is pattern size, right? And store it in temp. So how does temp looks like? In first iteration, it looks like AABA, then ABAA, then BAAC, right? And so on. Now, since we got the temp equal to size of pattern, right? We are comparing if temp is equals to pattern. If yes, then we are storing it in a result. Now, after this loop is executed, whatever indices are stored in result, we are simply returning it. Simple. Now, what will be the time complexity for this approach? Here, we are running a loop from 0 to m minus n, which will be approx O of m, which is text size. And inside, we are taking a substring from text, right, of length n. So, it will be O of n. So, together, the time complexity will be O of m cross n. Simple. And now, what will be the space complexity for this approach? Here, in every iteration, we are taking a substring of length n and storing it in temp, right? So the space complexity will be O of n, right? So this is a brute force approach that comes in our mind, right? Now, if you try to submit this problem, it will give time limit exceed because the constraint are 10 to the power of 6 for both m and n. So 10 to the power of 6 into 10 to the power of 6 will be 10 to the power of 12, which will give us P early, right? Now, we'll optimize our time complexity from m cross n to O of m plus n by using KMP algorithm. Okay, so let's see how KMP algorithm works. So, before understanding KMP algorithm, let's see what was going wrong with our brute force approach. So, we had two things, text and pattern, and we were considering every possible substring of pattern length from text. That is, we were first taking this window, and we were matching that window with our pattern. So if I show it again, so first we were matching this pattern with this string, right? If it was a match, then we were storing the starting index in our result, right? And we were moving this pattern one step ahead, right? And again, we were checking and moving, right? Now, if you guys observe carefully, we were matching this pattern with this much window of text, right? And it got matched. So this pattern got matched till this segment, right? Starting from here. Now, after we matched, we were moving our window by one step ahead, right? So we moved our window one step ahead. But do you think this makes any sense? No, right? Because we already have matched this character with this character and we have shifted this pattern one step ahead. So when we shifted this pattern one step ahead, the whole placement of the both characters have also been changed, right? But if you would have started directly from here, that is from this segment, then we might have chance to match the pattern again. So it's waste matching from here or here or here, right? Which was simply increasing our time complexity. We would have started directly from here. So this is one observation, right? Where we match the pattern with this segment of text. And after we matched it, instead of moving one step ahead, we moved it to this part. So behind the scenes, we had stored one pattern that when we move this window to here, then there is no chance of the pattern getting matched. So we as a human intelligently started patching from here, right? So this is the second example where our text is A P and our pattern is A B. Okay. So if we start matching the pattern again, I take the pointers. We are matching this character with this character. That this got matched. Okay. So we'll match this character and this character. Both A and A got matched. Okay. Now we are matching this character with this character. Right. Here our A didn't match with our B. So what we were doing in our conventional method, we were starting from 1th index, right? Since we have started here from 0th index, now we will start from 1th index. But in our pattern, we have come till index number 2. So when again we were starting from index number 1, but our pointer in pattern is at index 2. So when we are starting again from index number 1, we were resetting this whole pointer to again to index 0, which is wrong. Why? Because only this character have mismatched, right? But previously what we have matched, this part and this part, is still valid, right? Whatever we have computed in the past is valid. That is, this A is still valid, right? That means only this character got mismatched, right? This A is still valid. This A are still matching, right? So instead of bringing the pointer to again index number 0, we can bring it to index number 1, right? Because this character and these characters are both matching. So this is the intuition of KMP's algorithm. Now suppose if you have a string where you have shown a pattern and you have some extra characters and again you have a pattern. Okay. So after this pattern, there's an extra character here which got mismatched with the text. So instead of bringing the pointer again to here, you can bring it to here, right? And you start computing your string matching. Simple. So that's what we apply in our pattern. That is, for the first character as a pattern, this is the first occurrence. So we can ignore this. But when we see this we have already seen here. So instead of bringing the pointer from here directly to here, we can bring it here because these both are contributing the same, right? So for this set of substrings in KMP algorithm, we generally call it as longest prefix suffix because for AA, the longest prefix is A and the longest suffix is A and the length of each longest prefix suffix is 1. So if we take AA is a longest prefix suffix of length 1. Now why it is of length 1? Because if we take this string, this is a prefix of 1 length, right? And if we take this prefix, this is a suffix of length 1. So this is a longest prefix suffix of length 1. Simple. So this way KMP algorithm works. In our brute force approach, we are directly bringing our pointer to starting index. But in KMP algorithm, we recognize the pattern, and instead of starting again from the start, wherever the latest pattern has been matched, so we'll bring our pointer to that part instead of backtracking it to the starting, right? So to smartly backtrack to the particular position, instead of starting it from 0th index, we need to store it, right? We need to store the pattern, right? So that will create an LPS array of same size of pattern, and will store the index. That is, if we are at this index, at which index we need to backtrack, either to starting index or to the particular index where our LPS pattern have been matched, right?
So let's see how we can generate LPS array.
Now let's consider the pattern as AAB, and there's an LPS array that we need to calculate. So we can easily backtrack, right? And there's a length variable which is initialized to 0, right? Now we'll see what is the significance of this length variable. So we'll start from index number 0. At index number 0, the character is A. So we'll put the value as 0 here. Now why did we put 0 here? Because this is a starting character and we don't have any previous characters to backtrack, right? So that's why I have put the 0 here. Now at index number 1, the character is A, right? Now we'll check this A with this A. Now why did I consider this A? Because the index of this A is 0 and the value in our length is 0, right? So we are comparing this A with this A. Now since both of these A are equal, so I'll increment the value of the first index to 1, okay? And also simultaneously increase this value to 1. Now, what this part signify? If we take this much substring, that is A and A. Now, what is the longest prefix for this A? This A, right? And what is the longest suffix for this A? This A, right? And what is the length of longest prefix suffix? It is 1, right? So that's why we got 1 here, okay? Now, at index number 2, the character is B, right? Now, we'll try to match this character with the character that is present at this length, okay, which is A. So if we are matching this both A and B, it is not equal, right? So we'll try to shrink the space. Now when shrinking the space, this length will become 0, right? Now after the length got shrinked, we'll match this character with the element at this index, which is nothing but A. So when we are matching this A and B, again it is not equal, right? So we can simply assign the value as 0 and move our index to the next position, okay? So if we consider this much window, which is nothing but AAB, for this character, we try to assume this as a longest prefix, right? But this is not a longest prefix. So what did we do? We try to shrink this window from here till here. That's why our index from 1 got to 0. Now we checked for this character whether this is the longest prefix. No. So we again need to shrink this window, but there's nothing shrinking here. So we simply moved our pointer. But suppose we had B here. Now we try to check this character for this window, right, which is not the longest prefix. So we stringed it. Now for this character, for this window, it is a longest prefix, right? Both are matching. So we can increment the length to 1. Now you understood what is the significance of this length. We'll start with the maximum window. Then we'll shrink it until we don't find the match. If we find a match, whatever length we are at, we can simply assign the value. But if it is becoming 0, then there is no catch of shrinking it more, right? So we can move our pointer to next position and assign 0 there. Simple. Now we'll try to match this character with the character at index number 0, which is A, right? So both got matched. So first we'll increment our length by 1 and assign it here. The value will be 1. Now what does this 1 represent? If we consider this window, that is AABA, right? Now for this character, what is the longest prefix? It is this A, right? So the length is 1. And for this character, what is the longest suffix? It's A, right? So that's why the length of longest prefix and suffix is 1. Simple. Now at index number 4, the character is A. Okay, so we'll try to match this A with the element at index number 1, which is A. So this both A and A got matched. So we'll increment the value to 2 Okay, and we'll assign the 2 here. And for this substring, the length of longest prefix and suffix is 2. That is, if we consider this is the length of longest prefix, and if we consider this is the length of longest suffix. Okay. Now at index number 5, the character is B. Now we'll try to match this B with the element at index number 2, which is this B. Okay. So both got matched, right? So we'll first increment our length variable to 3 and assign the value here, that is 3. Now what does this 3 represent? For this pattern, if we check properly, this is the longest prefix for this, and this is the longest prefix for this, and both are matching, right? So this way we have generated our longest prefix suffix, right? So with this, our step number 1 is complete, that is to generate longest prefix suffix. Now once we generated our longest prefix suffix, the further computation is very easy. So here's the step number 2, where the text is AAB and the pattern is AAB, and I have already generated LPS for this, which is very simple, right? So we'll start at index 0 in text and index 0 at pattern. Now we'll check whether A is equals to A, right? So we'll move both the pointers. So this pointer will move by 1 step, this pointer will move by 1 step, right? Now again, this character and this character is equal. So we'll move both the pointers by 1 step. So this will move 1 step, this will move 1 step, right? Now we'll check whether this A is equals to this B. No. So do we need to backtrack again to index 0? No. We'll check. Check in our LPS array. We are at index number 2, right? And we need to check for the longest prefix suffix. So we'll jump 1 step behind and check what is the index that we need to jump. It is index number 1, right? So we'll jump at index number 1. So again, we'll resume our computation from index number 1 instead of going to index number 0. Simple. And this pointer will never move backward because we have already matched this A with this A. Simple. Now we'll try to match the character at index number 3 with the pattern in index number 2. Again we see both A and B are not equal. Now again we are at since index number 2, so we'll ask to previous index. At what index we need to jump? Again it is 1, right? So we'll jump to index number 1. So finally at index number 4 in the text and index number 2 in the pattern, we'll check whether B and B are equal. Yes, it's equal. So this pattern and this pattern is matched. So this way, in only one iteration in our text, we have got our pattern matched, right? Now we need to send our index. So how do we send our index? We are at index number 4, right? And the starting index is 2. Now how can we get this 2? Now if we take this index, which is 4, and subtract it with the index that we are at in the pattern, that is this 2, right? So what do we get? We get 2. And where did this pattern got matched from? This 2 index, right? Which is nothing but this AAB and this AAB, right? So this way we can generate our index and simply we can store this index in our result. So this was the whole KMP algorithm. Only generating the LPS array was bit tricky and not that intuitive. But after you get your LPS array, you have seen how easy it is to match the pattern from this text. Simple. So with these 2 steps, we can solve the problem. That is, in step number 1, we need to generate our LPS array. And after generating this LPS array, in step number 2, we can use this LPS array to get our pattern matched. Simple. Now let's see the code. So here's the code in C++. So firstly, I have taken the pattern size and the text size. And here I have created an array of LPS, which is of same length of pattern size. Okay, and initialize every variable to 0. And here I have created a variable length and assigned value 0, right? And I'm starting from index number 1. Why? You know, because at index number 0, we don't have any chance to backtrack, right? So here we are generating our LPS array. For that, till our I less than n, that is still we don't compute our whole pattern. So here I'm checking whether the pattern at ith index is equals to pattern at length, right? If it is equal, first I'm incrementing the length, then I'm assigning the length to the LPS of I and I'm incrementing the I pointer. But if the pattern is not matching, what we were doing? We are taking length, decrementing it by 1 and checking what is the value present at the LPS of length, right? And reassigning it back to length. But this is only possible if our length is greater than 0. Why? Because we are doing length minus 1. Suppose if the length is 0, then we can't check back again the same condition, right? So if only the length is 0, then we are reassigning our length variable by checking the LPS of length minus 1. But if it is not the case, then there's no chance we have pattern matched. So we are simply incrementing our I pointer. So with this, we have executed our step 1, that is generating LPS array. And after generating LPS array, it is simple, right? Here I am doing the pattern matching. For that, I have taken the result variable to store the indices and again reset the I value to 0 because here the I value have been manipulated, right? And initialize j value to 0. Right, now while j is less than m, that is while j pointer doesn't surpasses the whole text size, first I am checking whether text of j is equals to pattern of I. If both the characters are matching, then I'm simply incrementing I pointer and j pointer. But if it is not the case, then we need to move our index to appropriate position, not at 0th index, right? If it is 0th index, well and good. But if it is not 0 index, at least greater than 0 index, right? So for that, I'm checking again whether I is greater than 0. If yes, then I'm reassigning I with the LPS of I minus 1. But if it is not the case, that is I is less than 0, then we can simply increment our j pointer. Now after executing this both if and else, I am checking whether I is equals to n. That is whether I has reached the last position of array. If it is the case, then simply I am storing the starting index in the result, and you know how to get the starting index. Simply subtract j with I, or we can take n because both I and n are equal, so I have taken I. Simple. Now after pushing the index in the result, I am updating my index to LPS of I minus 1 to check for other patterns in the future string. Okay. So after this whole execution, we'll get our result ready and we'll return the result. So this is a two-step process that we have understood successfully, right? Now what will be the time complexity for this approach? Here we are generating LPS array, that is while I is less than n, where n is pattern dot size. So generating LPS array will take the time complexity of O of n, right, where n is pattern size. And here we are running a loop till j is less than m, where m is text size. So for this, the time complexity will be O of m. So overall the time complexity will be O of n plus m. Simple. And what will be the space complexity for this approach? Here we have taken an LPS array of size n, which is pattern size, and we have created a result vector. But this result vector we don't count because the problem itself wants us to return a vector of int, right? And apart from this vector, we have just created variables. So the space complexity will be O of n, where n is size of pattern. So I hope you guys like this video. I tried to explain KMP algorithm as detailed as possible. So see you guys in tomorrow's video. Till then, stay safe, stay happy, and peace.